So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's light hitting your eyes. Maybe it's the soft glow of a lamp. Maybe it's the blue haze of a screen. Maybe it's just the faintest sliver of streetlight slipping through a curtain. That light, that ordinary, unremarkable thing you barely think about, that light almost broke physics. It took some of the smartest people who ever lived and tied them in knots for decades. And the story of how they untangled it, how they followed that thread all the way down into the fabric of reality itself, is one of the most extraordinary stories in the history of human thought. It's the story of quantum physics. And it starts, like a lot of good stories, with someone staring at something hot and glowing and asking a question that nobody could answer. Let's go back. Way back. It's the late 1800s, and if you were a physicist at that time, you'd be feeling pretty good about yourself, pretty confident. The world made sense. Newton had given us mechanics, the laws of motion, gravity, the way objects move and collide in orbit. Maxwell had unified electricity and magnetism into one beautiful framework and shown that light itself was an electromagnetic wave. Thermodynamics was well understood. The periodic table was filling in. There was this widespread feeling, this almost smug sense, that physics was essentially done. That the big questions had been answered, and all that remained was refining measurements to a few more decimal places. Lord Kelvin, William Thomson, one of the towering figures of British science, is often credited with saying something along the lines of, "There is nothing new to be discovered in physics now. All that remains is more and more precise measurement." Whether he actually said exactly that is debated, but the sentiment was real. It was in the air. Physics was a finished building, and they were just polishing the floors. Except there were these two little problems. Kelvin himself actually referred to them as two small clouds on the horizon of physics. Two things that didn't quite fit. Two loose threads that, when pulled, would unravel the entire tapestry. One of those clouds had to do with how light travels through space, which would eventually lead Einstein to special relativity. But the other had to do with something deceptively simple. It had to do with how hot things glow. Think about a piece of metal. You heat it up. At first, it just gets warm, and you can feel the heat radiating off it. That's infrared radiation, invisible to your eyes but real. Keep heating it. Eventually, it starts to glow a dull red. Hotter still, and it turns orange, then yellow, then white hot. You've seen this if you've ever watched a blacksmith work, or even just looked at the coils inside a toaster. The color of the glow changes with temperature in a very predictable, very specific way. Physicists had been studying this carefully, and they had a name for the idealized version of this problem. They called it black body radiation. A black body is just a theoretical perfect absorber and emitter of radiation, something that doesn't reflect anything, just absorbs all the energy that hits it and re-emits it based purely on its temperature. It's an idealization, but you can get pretty close to one in a lab. A small hole in the side of a heated oven, for instance, acts almost exactly like a black body. The radiation coming out of that hole has a very characteristic spectrum, a specific distribution of wavelengths, a specific shape to the curve when you plot intensity against frequency. And here's the thing. They could measure that curve beautifully. Experimentalists had mapped it out with great precision by the 1890s. They knew exactly what the curve looked like at every temperature. But when theorists tried to derive that curve, tried to start from the known laws of physics and calculate what the curve should be, they couldn't do it. They could get parts of it right. There was a formula by Lord Rayleigh and James Jeans that worked pretty well for long wavelengths, for the low-frequency end of the spectrum. But as you move toward shorter wavelengths, toward the ultraviolet, Their formula didn't just get a little wrong. It went to infinity. It predicted that a hot object should radiate infinite energy at high frequencies. Infinite. Which is obviously catastrophically wrong. You'd be dead right now if it were true. Every warm object in the universe would be blasting out infinite ultraviolet and gamma radiation. They called this the ultraviolet catastrophe, and it's a great name because it really was a catastrophe, not a physical one, but an intellectual one. It meant something was deeply, fundamentally wrong with the way physics understood the interaction between matter and radiation. So that's the scene. It's the turn of the century, and this problem is sitting there like a splinter in the mind of every theoretical physicist in Europe. And the person who finally pulled it out was a meticulous, conservative, almost reluctant revolutionary named Max Planck. Let's talk about Planck for a second, because he matters enormously, and he's not quite the figure most people picture when they think of a scientific revolutionary. He wasn't young and brash. He wasn't an outsider. He was a thoroughly establishment German professor, formal, careful, deeply respectful of tradition. Born in 1858 in Kiel, into an academic family. His father was a law professor. His grandfather and great-grandfather had been theology professors. Planck was the kind of person who believed in order, in the rightness of established institutions, in doing things properly. When he was a young man considering a career in physics, one of his professors, Philipp von Jolly in Munich, actually advised him against it, told him that physics was essentially complete, that there was nothing significant left to discover. Planck went ahead anyway, not because he wanted to overturn the world, but because he found the existing laws beautiful and wanted to understand them more deeply. He was drawn to thermodynamics in particular, to the elegant certainty of its laws. And that's what makes what happened next so remarkable. Because Planck didn't set out to start a revolution. He was trying to solve a specific, well-defined problem, the black-body radiation curve. And he was trying to do it using the most conservative methods available to him. He wanted to make classical physics work. He spent years on it. By October of 1900, Planck had managed to find a mathematical formula that fit the experimental data perfectly, beautifully. Every point on the curve, at every temperature, matched. But here's the thing. He'd found the formula first, by a kind of inspired interpolation, by fiddling with the math until it worked. He didn't yet have a physical explanation for why it worked, and that bothered him deeply. He was a theorist. He needed to derive the formula from first principles, from some physical picture of what was actually happening inside that glowing cavity. So he went looking for a derivation, and in December of 1900, this is the moment, this is the one that changes everything. He presented a derivation to the German Physical Society. But to make the math work, he'd had to do something strange, something he himself found deeply uncomfortable. He had to assume that energy wasn't continuous. Now, let me explain what that means, because it's the crux of everything. In classical physics, energy is smooth. It flows. You can have any amount of it. Think of it like water. You can pour a little or a lot, and there's no minimum amount. You can always pour just a tiny bit less. Energy, in the classical view, is infinitely divisible. But Planck found that the only way to get his formula to work, the only way to avoid that ultraviolet catastrophe, was to assume that the energy of the oscillating atoms in the walls of the black body could only come in discrete chunks, little packets. He called them quanta, from the Latin word for how much. Each quantum of energy was proportional to the frequency of the radiation. High frequency, big quanta, low frequency, small quanta. And the constant of proportionality, the number that linked energy to frequency, is what we now call Planck's constant. It's one of the most fundamental numbers in all of physics. It's tiny, about 6.626 times 10 to the negative 34 joule seconds. But it's not zero, and that makes all the difference. Here's an analogy that might help. Imagine you're on a ramp versus a staircase. Classical physics says energy is like a ramp. You can stand at any height, any position, smoothly anywhere you like. What Planck was saying, at least mathematically, was that energy is more like a staircase. You can stand on this step or that step, but not in between. The steps are incredibly tiny, so tiny that in everyday life you'd never notice them, just like you'd never notice individual atoms in a smooth table. But they're there, and at the atomic scale, they matter enormously. Now here's what's fascinating about Planck. He didn't really believe it, or rather, he thought it was a mathematical trick, a computational device that happened to give the right answer. He didn't think energy was actually quantized in any deep physical sense. He figured someone would eventually find a proper classical derivation that gave the same result without this awkward assumption. He spent years trying to undo his own discovery, trying to find a way back to the smooth, continuous world of classical physics. He never found one. And you can understand his reluctance. Think about what he was really saying, even if he didn't fully appreciate it yet. He was saying that at the deepest level, nature is not smooth. It's granular. It comes in pieces. That's not just a minor technical adjustment. It's a completely different picture of reality. It's like discovering that what you thought was a continuous ocean is actually made of individual droplets, and the dropletness of it actually matters for how waves behave. But in 1900, most physicists treated Planck's quantum hypothesis the same way Planck did, as a clever mathematical trick, not a statement about nature. The real earthquake was still a few years away, and it would come from a young man working in a patent office in Bern, Switzerland, who would take Planck's idea far more seriously than Planck himself ever intended. Someone who would look at another stubborn puzzle, a different experiment that classical physics couldn't explain, and say, no, the quanta aren't just a trick, they're real. Light itself comes in packets. That young man, of course, was Albert Einstein, and the puzzle he was looking at had to do with what happens when you shine light on a piece of metal, something called the photoelectric effect. It had been noticed back in 1887 by Heinrich Hertz, ironically while he was doing experiments that confirmed Maxwell's wave theory of light. Hertz noticed that when ultraviolet light hit a metal surface, it could cause sparks to jump more easily. Something about the light was knocking electrons loose from the metal. Later experiments, particularly by Philippe Lenard around 1902, pinned down the details, and those details were deeply strange. Strange in a way that classical wave theory simply could not explain. The energy of the ejected electrons didn't depend on how bright the light was. It depended on the color, on the frequency. Dim violet light could kick out fast electrons, but no amount of blazingly bright red light could kick out any electrons at all. If light were a wave, like everyone believed, this made no sense. A brighter light means a bigger wave, more energy arriving at the surface. You'd expect brighter light to always win, regardless of color. But it didn't. There was a threshold frequency below which nothing happened, no matter how intense the light. And above that threshold, even the faintest glimmer would start producing electrons immediately. No delay, no buildup. Einstein looked at this in 1905, and he saw something that most people weren't willing to see. He saw that Planck's quanta weren't just a bookkeeping trick for radiation inside a hot cavity. He saw that light itself, the actual beam of light traveling through space, was made of discrete little packets of energy. Each packet carried an amount of energy equal to Planck's constant times the frequency of the light. One packet, one quantum. And when that packet hit an electron sitting in the surface of a metal, it was an all-or-nothing transaction. The entire packet got absorbed by one electron. If that packet carried enough energy to overcome the force holding the electron in the metal, a quantity physicists call the work function, then the electron would fly free. If the packet didn't carry enough energy, nothing happened. The electron just sat there, no matter how many low-energy packets rained down on it. Think about that for a second. Imagine you're trying to knock a coconut off a high shelf by throwing balls at it. If you throw ping pong balls, it doesn't matter how many you throw or how fast you throw them. Each individual ping pong ball is too light to dislodge the coconut. But one well-thrown baseball will do the job. That's essentially what Einstein was saying about light and electrons. A red photon. And Einstein would later help give them that name, photons. A red photon is like a ping pong ball. It just doesn't carry enough energy per packet. A violet photon is like a baseball. It carries more energy because violet light has a higher frequency, and energy equals Planck's constant times frequency. So one violet photon can knock an electron free, and a red photon simply can't, no matter how many of them you pile on. This explained everything Leonard had observed. It explained why there was a threshold frequency. Below it, individual photons didn't carry enough energy. It explained why brightness didn't matter below that threshold. More photons just meant more ping pong balls, and a million ping pong balls still can't do what one baseball can. It explained why, above the threshold, electrons appeared instantly even in dim light, because even one photon with sufficient energy could eject one electron the moment it arrived. No waiting, no accumulation. One photon in, one electron out. Einstein published this in March 1905 in a paper titled On a Heuristic Viewpoint Concerning the Production and Transformation of Light. And here's a detail that always gets me. Of all the papers Einstein published that miraculous year, 1905, the year he also gave us special relativity and the famous E equals mc squared, the photoelectric effect paper was the one he himself called revolutionary. He knew that saying light comes in particles was a radical claim. It was, in a way, reaching back 200 years to Newton, who had believed light was made of particles, what Newton called corpuscles. The entire 19th century had been spent proving Newton wrong about that. Young's double-slit experiment in 1801, Maxwell's equations in the 1860s, Hertz's experiments in 1887, all of it had built an airtight case that light was a wave. And now Einstein was saying, well, actually, it's also particles, not instead of also. That word also is doing a lot of heavy lifting, and it would take another 20 years before anyone really figured out what it meant. But we'll get there. Now, here's the thing about Einstein's photoelectric paper. Almost nobody believed him. Not at first. Even Planck, the man who had invented the quantum in the first place, thought Einstein had gone too far. Planck wrote a letter recommending Einstein for membership in the Prussian Academy of Sciences in 1913, and in that letter he praised Einstein's many contributions, but specifically said, and I'm paraphrasing only slightly, that Einstein's light quantum hypothesis shouldn't be held against him, because even the best minds sometimes overshoot. Planck was essentially apologizing for Einstein's most important idea. That's how uncomfortable the physics community was with the notion that light could be granular, but the experimental evidence kept piling up. Robert Millikan, an American physicist working at the University of Chicago, actually set out to disprove Einstein's equation for the photoelectric effect. He spent about a decade on meticulous experiments, from roughly 1905 to 1916, carefully measuring how the energy of ejected electrons varied with the frequency of incoming light. And what he found, somewhat to his own frustration, was that Einstein's equation was exactly right. Every single data point fell on the line Einstein had predicted. The relationship between photon frequency and electron energy was perfectly linear, with a slope equal to Planck's constant. Millikan published his results in 1916, confirming the equation while still insisting in his paper that Einstein's underlying theory of light quanta was probably wrong. He couldn't argue with his own data, but he didn't want to accept what it meant. Eventually, of course, he came around. Both men won Nobel Prizes. Einstein in 1921 for the photoelectric effect, Millikan in 1923 partly for his experimental verification of it. So by the early 1920s, physics was in this genuinely bizarre situation. Light behaved like a wave in some experiments. Interference, diffraction, all the things Thomas Young and Augustin Fresnel had demonstrated over a century earlier. And light behaved like a particle in other experiments. The photoelectric effect, and later, Arthur Compton's 1923 experiment showing that X-rays bounced off electrons exactly the way one billiard ball bounces off another, with momentum and energy conserved as if the X-ray were a little bullet. Wave or particle? The answer, maddeningly, seemed to be yes. But let's not get ahead of ourselves. Let's go back to around 1911 and talk about what was happening inside the atom, because that's where the quantum story gets really personal, really specific, and honestly, really beautiful. By this point, people knew atoms existed. That debate was more or less settled, thanks in part to Einstein's 1905 paper on Brownian motion, which showed that the jittery dance of pollen grains in water could be explained by collisions with invisible molecules, and people knew atoms contained electrons, those tiny negatively charged particles that J.J. Thomson had identified in 1897. But what did an atom actually look like? Thomson had proposed what people affectionately called the plum pudding model, a blob of positive charge with electrons embedded in it like raisins in a pudding. It was a reasonable guess. It was also completely wrong. The man who destroyed the plum pudding was Ernest Rutherford, a New Zealander working at the University of Manchester. Rutherford was a big, loud, boisterous experimentalist, the kind of physicist who distrusted fancy mathematics and trusted what he could measure. In 1909, he set two of his students, Hans Geiger and Ernest Marsden, to work on an experiment that seemed almost routine. They fired tiny, fast-moving alpha particles, which are basically helium nuclei, little bundles of positive charge, at a thin gold foil, and they watched where the particles went after passing through. Most of them sailed straight through, which was expected. The gold foil was thin enough that you'd expect the alpha particles to plow through like bullets through tissue paper. But some of them bounced back. Not just deflected a little, some of them came almost straight back toward the source. Rutherford later said, "It was as if you fired an artillery shell at a piece of tissue paper and the shell came back and hit you." That's how shocking it was. What it meant was that almost all the mass of the atom and all of its positive charge was concentrated in a tiny, dense core. What Rutherford called the nucleus. The atom was mostly empty space, with electrons orbiting far away from this dense center, like planets orbiting a distant sun. The nuclear model of the atom was born. But here's where things go wrong, and this is important. According to classical physics, Maxwell's equations specifically. An electron orbiting a nucleus should be constantly radiating energy. It's an accelerating charge because circular motion is a form of acceleration, and accelerating charges emit electromagnetic radiation. That's just what Maxwell's theory says, and Maxwell's theory was incredibly well tested. So the electron should be losing energy continuously, spiraling inward, radiating light at ever-increasing frequencies, and crashing into the nucleus in a tiny fraction of a second. The math said atoms should collapse almost instantly. Every atom in the universe should be unstable. Obviously, atoms don't collapse. You're lying there right now, made of trillions of them, all perfectly stable, and they've been stable for billions of years. So something was deeply, fundamentally wrong with the classical picture of the atom. Rutherford's model was a triumph of experimental physics and a catastrophe for theoretical physics, all at the same time. Enter Niels Bohr. If Planck was the reluctant grandfather of quantum theory, and Einstein was its bold young advocate, Bohr was the person who brought quantum ideas inside the atom itself. Bohr was Danish, born in Copenhagen in 1885, the son of a physiology professor. He was a quiet, thoughtful man, famously difficult to understand when he spoke, because he mumbled and trailed off mid-sentence, always chasing the next thought before he'd finished expressing the current one. He played soccer, quite seriously in fact. His brother Harold played for the Danish Olympic team. But Niels was drawn to physics, and in 1911, he traveled to England to work with Thomson at Cambridge. That didn't go especially well. Bohr had a habit of pointing out errors in Thomson's work, which, accurate or not, didn't endear him to his host. So Bohr moved to Manchester to work with Rutherford, and that's where everything changed. Bohr looked at Rutherford's atom, and he saw the same problem everyone else saw. The electron should spiral in, and the atom should collapse. But instead of despairing, he did something audacious. He simply declared that certain orbits were special. He said electrons could only occupy specific orbits at specific distances from the nucleus, and while they were in those orbits, they didn't radiate energy. They just didn't. He couldn't explain why. He simply postulated it as a rule. The electron sits in its orbit, stable, silent, not radiating, in flat contradiction of Maxwell's equations. And then, when an electron jumps from one allowed orbit to another, from a higher orbit to a lower one, it emits a single quantum of light, a photon, whose energy equals the difference between the two orbits. Jump down, emit a photon. Absorb a photon with exactly the right energy. Jump up. This was Bohr's atomic model, published in 1913, and it was half genius and half duct tape. The genius part was that it worked, spectacularly for hydrogen. For decades, people had known that hydrogen gas, when you heat it up or run electricity through it, glows with very specific colors. Not a smooth rainbow, but sharp, distinct lines, particular wavelengths of light and nothing in between. Johann Balmer had found a mathematical formula for some of these lines back in 1885, but nobody knew why the formula worked. Bohr's model explained it. Each line corresponded to an electron jumping between two specific orbits. The frequencies matched Balmer's formula exactly. Bohr could even calculate the size of the hydrogen atom, and he got the right answer. But the duct tape part was that Bohr had no real justification for why only certain orbits were allowed. He imposed a rule. The angular momentum of the electron had to be a whole number multiple of Planck's constant divided by 2pi. But he couldn't derive that rule from anything deeper. It was an assertion, a patch, a brilliant guess that happened to give the right answers for hydrogen, but struggled with more complex atoms, and it raised as many questions as it answered. Why those orbits? What happens to the electron between orbits? Does it somehow teleport from one to the other without passing through the space in between? These questions would haunt physics for the next decade, and the person who would begin to answer them was a French prince with a doctoral thesis so strange that his examiners didn't know what to make of it. A thesis that proposed something even wilder than anything Einstein or Bohr had suggested. If light, which everyone knew was a wave, could behave like a particle, then maybe particles, electrons, things with mass, things you could weigh, could behave like waves. That was de Broglie's radical idea. Louis de Broglie, and by the way, it's pronounced de Broglie because French, came from an aristocratic family. He was actually a prince, the 7th Duc de Broglie, and he'd originally studied history before switching to physics, partly inspired by his older brother Maurice, who was doing interesting work with X-rays. And in 1924, Louis submitted his doctoral thesis at the University of Paris, and in it he proposed something that sounds almost absurdly simple, but turned out to be one of the most important ideas in the history of physics. He said, if light can be both a wave and a particle, then why can't matter be both a particle and a wave? He didn't just say it philosophically. He gave it a precise mathematical form. He said that any particle, an electron, a proton, a baseball, U, has an associated wavelength, and that wavelength equals Planck's constant divided by the particle's momentum. That's it. One elegant little equation. Lambda equals h over p. The wavelength of a particle is Planck's constant divided by its momentum, which is its mass times its velocity. And here's what's beautiful about it. It immediately explains Bohr's mysterious rule about allowed orbits. Think about it this way. If an electron is actually a wave and it's traveling around the nucleus in a circular orbit, then for that wave to be stable, for it to not destructively interfere with itself, it has to fit perfectly around the orbit. The circumference of the orbit has to be a whole number of wavelengths. 1 wavelength, 2 wavelengths, 3, 4, but not 1.5, not 2 1/4. Because if the wave doesn't close on itself neatly, it cancels out. It's like wrapping a vibrating string into a circle. The vibration only sustains if the loop accommodates complete waves. And when you do the math, when you set the circumference equal to a whole number times the de Broglie wavelength, you get exactly Bohr's quantization condition. Exactly. The angular momentum comes out as a whole number multiple of h over 2 pi, just like Bohr had postulated out of thin air. But now there was a reason. The electron could only exist in orbits where its wave nature allowed it to sustain a stable standing wave. The quantization wasn't arbitrary. It was a consequence of wave mechanics. Now, de Broglie's thesis committee reportedly didn't quite know what to do with this. The story goes that his advisor, Paul Langevin, was impressed but uncertain, so he sent a copy to Einstein. And Einstein's response was essentially, "This young man has lifted a corner of the great veil," which is about as strong an endorsement as you can get from Einstein. The thesis was accepted, and de Broglie got his doctorate, and in 1929 he won the Nobel Prize for it. But at the time, in 1924, it was still just a theoretical proposal. A beautiful idea, but was it true? Did electrons actually behave like waves? The answer came in 1927, and it came from 2 separate experiments conducted independently on 2 different continents. The first was by Clinton Davison and Lester Germer at Bell Labs in New York. They were firing electrons at a nickel crystal and measuring how the electrons scattered. and they noticed something strange. The electrons weren't scattering uniformly. They were producing a pattern of strong and weak reflections at specific angles, exactly the kind of pattern you'd expect from wave diffraction. Exactly the kind of pattern that X-rays produce when they bounce off crystal lattices. The spacing of the nickel atoms was acting like a diffraction grating for the electrons, and the pattern matched de Broglie's predicted wavelength perfectly. And here's a wonderful detail about this experiment. It partly happened by accident. Davison and Germer had been doing electron scattering experiments for a while, getting unremarkable results, when their vacuum chamber cracked. Air rushed in, the nickel target oxidized, and to fix it, they heated the nickel to high temperature. What they didn't realize was that the heating process caused the nickel to recrystallize into large, orderly crystal domains. When they resumed the experiment with this accidentally improved target, suddenly the scattering pattern changed dramatically. Sharp peaks appeared at specific angles. They were seeing electron diffraction, and they almost missed it. If that vacuum tube hadn't cracked, if they hadn't heated the nickel, the crystal structure wouldn't have been regular enough to produce a clear diffraction pattern, and the discovery might have been delayed by years. Meanwhile, across the Atlantic, George Paget Thomson, and yes, that's J.J. Thomson's son, was independently demonstrating electron diffraction by firing electrons through thin metal foils and observing ring patterns on photographic plates. The same kind of ring patterns you get when you shine light through a fine mesh. Father discovers the electron as a particle. Son proves it's also a wave. There's a kind of poetry in that. Both Davison and Thomson shared the 1937 Nobel Prize for experimentally confirming de Broglie's hypothesis. So by the late 1920s, the situation was this. Everything is both a wave and a particle. Light, which classical physics said was purely a wave, also behaves like a stream of particles. Electrons, which classical physics said were purely particles, also behave like waves. And this isn't some exotic, marginal effect. It's fundamental. It's how nature actually works. But what does it mean? What is this wave? When we say an electron has a wavelength, what exactly is waving? This is where things get really deep, and where the next generation of physicists, young, brilliant, and sometimes barely out of their 20s, would construct the full mathematical framework of quantum mechanics in a burst of creativity that rivals anything in the history of science. It happened fast, mostly between 1925 and 1927, and it happened in two seemingly different ways, developed by two very different people. The first was Werner Heisenberg. In 1925, Heisenberg was 23 years old, working as an assistant to Max Born in Göttingen, Germany. He'd been struggling with the problems of atomic physics, trying to calculate the intensities and frequencies of spectral lines for atoms more complex than hydrogen, and getting nowhere with Bohr's orbital model. And Heisenberg made a radical decision. He decided to stop trying to picture what electrons were doing inside atoms. Stop trying to imagine little orbits, little trajectories, little planetary paths. Instead, he would focus only on what could actually be observed, the frequencies and intensities of the light that atoms emit and absorb, the things you could actually measure. He was suffering from terrible hay fever that spring, and he retreated to the rocky island of Helgoland in the North Sea to recover, away from pollen, away from distractions. And there, working alone on this barren island, he developed a new mathematical framework. Instead of describing electron positions and orbits, he arranged the observable quantities, transition frequencies and amplitudes, into arrays of numbers, tables where each entry corresponded to a transition between two energy states. He figured out rules for how to multiply these arrays together, and he noticed something strange. The order of multiplication mattered. If you multiplied array A by array B, you got a different result than if you multiplied B by A. This was deeply unusual. Regular numbers don't do that. 3 times 5 is the same as 5 times 3. But Heisenberg's quantities didn't commute. When he brought this work back to Göttingen, Max Born looked at the mathematics and recognized something. These arrays, these tables of numbers with their strange multiplication rules, they were matrices. Mathematicians had been studying matrices for decades, but physicists rarely used them. Born, together with his student Pascual Jordan, helped Heisenberg formalize the whole thing into what became known as matrix mechanics. It was abstract, it was unfamiliar, and most physicists found it deeply unintuitive. You couldn't visualize anything. There were no orbits, no waves, no pictures at all, just arrays of numbers obeying algebraic rules. It worked, it gave the right answers, but it felt like doing physics blindfolded. And then, almost simultaneously, a completely different approach appeared, from a completely different kind of physicist. Erwin Schrödinger was Austrian, older than Heisenberg by more than a decade. He was 38 in 1925, and temperamentally his opposite. Where Heisenberg was willing to abandon visualization entirely, Schrödinger craved it. He wanted a physics you could picture, a physics built on waves you could imagine propagating through space, and he took de Broglie's matter wave idea and ran with it. Over Christmas 1925, Schrödinger went to a villa in the Swiss Alps, Arosa, a ski resort in the mountains above Davos, and he brought along a mysterious companion whose identity has never been conclusively established, along with his notes on de Broglie's thesis. And over that holiday, in what might be the most productive vacation in the history of science, he derived his wave equation, the Schrödinger equation. It describes how a wave function, this mathematical object he called SI, evolves over time. And when he applied it to the hydrogen atom, treating the electron as a wave surrounding the nucleus, the allowed energy levels popped out naturally. No need to postulate quantized orbits. No need for Bohr's arbitrary rules. The quantization emerged from the mathematics of the wave equation itself, the same way that a guitar string can only vibrate at certain frequencies. Its fundamental and its harmonics, the boundary conditions, the requirement that the wave function be well behaved, that it not blow up to infinity, automatically selected only certain solutions, and those solutions corresponded to exactly the energy levels that Bohr had found. Physicists loved it. Schrödinger's wave mechanics was something you could work with, something you could visualize, or at least something that felt more familiar than Heisenberg's inscrutable matrices. Schrödinger himself was convinced that the electron literally was a wave smeared out in space around the nucleus, and that quantum mechanics could be understood in continuous, classical-feeling terms. He published a series of papers in 1926 that laid the whole thing out, and he also proved something remarkable. His wave mechanics and Heisenberg's matrix mechanics, despite looking completely different, were mathematically equivalent. They were the same theory wearing different clothes. Every result you could derive with one, you could derive with the other. But here's the thing. Even though the two formalisms were equivalent, the interpretation was fiercely contested. What was this wave function, this PSI? Schrödinger said it represented the electron itself, spread out like a cloud. But Max Born, back in Göttingen, proposed something far stranger. Born said the wave function doesn't tell you where the electron is. It tells you the probability of finding the electron in a particular place. Specifically, the square of the wave function's magnitude at any point gives you the probability density, the likelihood per unit volume that if you look for the electron right there, that's where you'll find it. The electron isn't smeared out. It's genuinely in one place when you measure it. But before you measure it, all you can know is probabilities. This was Born's probability interpretation, published in 1926, and it shook the foundations of physics in a way that still reverberates today. Because think about what it means. In classical physics, if you know the position and velocity of a particle right now, you can predict exactly where it will be at any future time. The universe is deterministic, like clockwork. But Born was saying that quantum mechanics is fundamentally probabilistic. Even if you know everything there is to know about a quantum system, even if you have the complete wave function, you still can't predict with certainty what you'll get when you make a measurement. You can only predict probabilities. And this isn't because your knowledge is incomplete or because your instruments aren't good enough. It's because nature itself doesn't determine the outcome until the measurement happens. Einstein hated this, absolutely hated it. This is where his famous line comes from. God does not play dice with the universe. He never accepted that the fundamental laws of physics could be probabilistic. He spent the rest of his life arguing that quantum mechanics must be incomplete, that there must be hidden variables, deeper layers of reality that, once discovered, would restore determinism. And Bohr, who became the chief philosophical defender of the new quantum mechanics, pushed back just as hard. Their debates, the Bohr-Einstein debates, would become legendary, stretching across conferences in the late 1920s and 1930s, with Einstein devising ever more ingenious thought experiments to show that quantum mechanics was inconsistent, and Bohr finding the flaw in each one, sometimes after agonizing all night. But before we get to those debates, there's another piece of the puzzle that fell into place in 1927, and it came from Heisenberg again. He was thinking about what it actually means to measure something at the quantum scale, to determine, say, the position of an electron. And he realized something profound, something that wasn't just a practical limitation, but a fundamental feature of reality itself, the uncertainty principle. And it's one of those ideas that sounds simple when you first hear it, but the deeper you go, the stranger and more beautiful it becomes. Here's what Heisenberg was wrestling with. Imagine you want to know exactly where an electron is. Well, to see something, you need to bounce light off it. That's how seeing works, whether you're looking at a baseball or an electron. But an electron is so tiny, so lightweight, that the very act of hitting it with a photon, with a particle of light, changes its motion. If you use a short wavelength photon, like a gamma ray, you get very precise information about where the electron is, because short wavelengths give you fine resolution. But here's the catch. Short wavelength photons carry a lot of energy and a lot of momentum. Remember that relationship from Compton's work. The momentum of a photon is related to its wavelength. So when that high-energy gamma ray smacks into the electron, it gives it a huge, unpredictable kick. You now know where the electron was, but you've completely scrambled its momentum. You have no idea how fast it's going or in what direction. Okay, so try the opposite. Use a long wavelength, low-energy photon, something gentle, something that barely disturbs the electron. Now you preserve good information about the electron's momentum because you haven't kicked it very hard. But long wavelengths give you terrible resolution. You can't pin down the electron's position precisely. It's like trying to locate a marble by gently tossing a beach ball at it. Sure, you won't disturb the marble much, but you also won't learn exactly where it is. And Heisenberg showed that this isn't a problem you can engineer your way out of. It's not about building better instruments. It's a fundamental trade-off baked into the fabric of reality. The product of the uncertainty in position and the uncertainty in momentum can never be smaller than a certain value. Roughly Planck's constant divided by 4 pi. You can make one of those uncertainties as small as you like, but only at the cost of making the other one larger. You cannot simultaneously know both the exact position and the exact momentum of a particle. Not because you're clumsy, not because your equipment is limited, but because the universe simply doesn't have definite values for both at the same time. Think about what that means. In classical physics, a particle has a position and a momentum at every instant. Those are real, definite properties that exist whether or not you're looking. Heisenberg was saying something far more radical. He was saying that at the quantum level, the very concept of a particle having a precise position and a precise momentum simultaneously doesn't apply. It's not that the electron has a definite position and you just don't know it. It's that the electron genuinely doesn't have a definite position when its momentum is well defined, and vice versa. The properties themselves are fuzzy, indeterminate, until a measurement forces one of them into focus, at the expense of the other. He published this in 1927, and it sent shock waves through physics. Not everyone understood it the same way, and in fact, Heisenberg and Bohr themselves had a rather intense disagreement about how to interpret the uncertainty principle. Heisenberg originally framed it in terms of the disturbance caused by measurement, the gamma-ray microscope thought experiment I just described. Bohr thought this was misleading because it made it sound like the electron really does have definite properties, and you're just messing them up by looking. Bohr wanted to emphasize that the indeterminacy is more fundamental than that. They argued about it, apparently quite emotionally. Heisenberg was reportedly in tears at one point. These were young men. Heisenberg was 25, grappling with ideas that were overturning centuries of physical intuition, and the pressure was immense. But eventually, their views converged into something broader, something Bohr called complementarity. And this became the philosophical backbone of what's known as the Copenhagen interpretation of quantum mechanics, named after Bohr's institute in Copenhagen, where so much of this thinking took shape. The basic idea of complementarity is that quantum objects have pairs of complementary properties, like position and momentum, or wave nature and particle nature, that cannot both be fully defined at the same time. They're not contradictory, they're complementary. You need both descriptions to get the full picture, but you can never see both simultaneously. Which aspect you observe depends on what kind of experiment you set up. So if you design an experiment to detect which slit an electron goes through in a double-slit experiment, you'll see particle behavior. The electron goes through one slit or the other, but you'll lose the interference pattern. If you don't try to detect which slit it goes through, you get the interference pattern, wave behavior, but you can't say which slit the electron went through. The experiment you choose to perform determines what kind of reality you see, and both are equally valid, equally real. Neither is more fundamental than the other. Now, this is where Einstein really dug in his heels. The Bohr-Einstein debates are some of the most fascinating intellectual exchanges in the history of science, and they played out primarily at the Solvay conferences, these elite gatherings of the world's top physicists, held in Brussels, funded by a Belgian industrialist named Ernest Solvay. The fifth Solvay conference, in October 1927, is probably the most famous scientific conference ever held. The photograph from that meeting is legendary. 29 attendees, 17 of whom were or would become Nobel Prize winners. Einstein, Bohr, Heisenberg, Schrödinger, Born, de Broglie, Dirac, Pauli, Lorentz, Curie. The roster reads like a hall of fame. And the real action happened not in the formal sessions, but at breakfast, in the hallways, over dinner. Einstein would come to breakfast each morning with a new thought experiment. some clever scenario designed to show that quantum mechanics was inconsistent, that you could, in principle, beat the uncertainty principle and determine both position and momentum precisely. And Bohr would spend the rest of the day, sometimes agonizing through the night, finding the flaw in Einstein's argument. By the next morning, Bohr would have his response. And each time, he found that quantum mechanics held up. Einstein's thought experiments, ingenious as they were, always contained a subtle oversight. One of the most famous examples came at the 6th Solvay Conference in 1930. Einstein proposed a thought experiment involving a box filled with radiation. A photon box, people called it. The box has a shutter controlled by a clock inside. At a precisely known time, the shutter opens briefly and lets out a single photon. You weigh the box before and after. Since the photon carries energy, and energy is equivalent to mass by E equals mc squared, the box should be very slightly lighter after the photon escapes. So now you know the exact time the photon was emitted, because you controlled the clock, and you know the exact energy of the photon, because you measured the mass difference. But the uncertainty principle says you can't know both the energy and the time of emission with arbitrary precision. There's an energy-time uncertainty relation, analogous to the position-momentum one. So Einstein was claiming he'd beaten the uncertainty principle. Bohr was reportedly shaken by this argument. He couldn't find the flaw at first. He spent a sleepless night working on it. And then, by morning, he had the answer. And it was devastating in its elegance. Bohr pointed out that when you weigh the box, you're measuring its position in a gravitational field. The box moves slightly on the scale. And here's the beautiful irony. By Einstein's own general theory of relativity, a clock's rate depends on its position in a gravitational field. A clock that's slightly higher in a gravitational field ticks faster than one that's slightly lower. So the very act of weighing the box, of letting it shift slightly in the gravitational field, introduces an uncertainty in the rate of the clock inside, which introduces an uncertainty in the time of the photon's emission. And when you work through the math carefully, this gravitational time dilation introduces exactly enough uncertainty to preserve the energy-time uncertainty relation. Einstein's own theory of general relativity saved quantum mechanics from Einstein's own attack. It's hard to overstate how remarkable that moment was. Einstein, the greatest physicist of his generation, arguably of all time, had devised the cleverest possible challenge to quantum mechanics, and the resolution came from his own greatest achievement. Bohr had used general relativity against its creator, and Einstein, to his credit, accepted that the argument was valid. He stopped trying to show that quantum mechanics was logically inconsistent, but he never accepted that it was complete. He shifted his strategy. Instead of trying to find contradictions within quantum mechanics, he began arguing that quantum mechanics, while correct as far as it goes, must be missing something, that there must be a deeper, more complete theory underneath. But let's step back from the philosophy for a moment, because while Bohr and Einstein were debating the meaning of quantum mechanics, other physicists were busy using it, and the results were spectacular. The late 1920s and 1930s were a golden age of applied quantum mechanics, a period when the theory was turned loose on problem after problem and kept delivering answers that matched experiment with stunning precision. One of the first great triumphs was understanding the structure of atoms beyond hydrogen. Bohr's old model had worked beautifully for hydrogen, one proton, one electron, but it failed miserably for anything more complex. Helium, with just 2 electrons, was already too complicated for the old approach. But with the full machinery of quantum mechanics, Schrödinger's equation, the probability interpretation, the uncertainty principle, physicists could finally tackle multi-electron atoms. The key insight was that electrons in an atom don't just occupy energy levels. They also have other quantum numbers describing their angular momentum, their orientation in space, and something entirely new called spin. Spin is one of those quantum properties that has no real classical analog. It was proposed in 1925 by two young Dutch physicists, George Uhlenbeck and Samuel Goudsmit, who were graduate students at the time. They suggested that the electron behaves as though it's spinning on its axis, like a tiny top, and this spinning gives it a small magnetic moment. But here's the strange part. The electron's spin can only take one of two values. It's either spinning one way or the other, with nothing in between. Spin up or spin down. And calling it spinning is really a metaphor, because if you try to calculate how fast the electron's surface would need to be moving to generate the observed magnetic moment, you get a speed faster than light, which is impossible. So the electron isn't literally spinning. Spin is an intrinsic quantum mechanical property that simply doesn't exist in classical physics. It's as fundamental to the electron as its charge or its mass, but it has no counterpart in the everyday world. And spin turned out to be the key to understanding one of the most important principles in all of physics, the Pauli exclusion principle, proposed by Wolfgang Pauli in 1925, just before quantum mechanics was fully formulated. Pauli was an Austrian theoretical physicist, brilliant and famously sharp-tongued. He once dismissed a colleague's paper by saying, "It's not even wrong," meaning it was so vague and muddled that it didn't even rise to the level of being testable. He was not someone you wanted reviewing your work unless you had thick skin, but his exclusion principle was a stroke of genius. It states that no two electrons in an atom can have the same set of quantum numbers. Each electron must be in a unique quantum state. And since the quantum state of an electron is described by four quantum numbers, the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number, this means each specific combination of those four numbers can be occupied by at most one electron. This is why atoms have the structure they do. This is why the periodic table looks the way it does. This is why chemistry works. Think about it. If electrons could all pile into the lowest energy level, every atom would behave roughly the same way. There'd be no chemistry, no molecules, no materials with different properties, no life. The exclusion principle forces electrons to stack up into higher and higher energy levels, filling shells and subshells in a specific order, and it's the arrangement of electrons in the outermost shell that determines an element's chemical behavior. Carbon acts differently from nitrogen, acts differently from oxygen, because they have different numbers of electrons in their outer shells, arranged according to the rules that quantum mechanics and the exclusion principle dictate. The entire periodic table, that beautiful organizing chart of all the elements, is essentially a map of quantum mechanical structure. And Pauli later showed that the exclusion principle applies not just to electrons, but to all particles with half-integer spin, particles called fermions, protons, neutrons, quarks. They're all fermions, and they all obey the exclusion principle. Particles with integer spin, photons, for example, are called bosons, and they follow completely different rules. Bosons are gregarious. They actually prefer to be in the same quantum state. This distinction between fermions and bosons turns out to be one of the deepest organizing principles in all of physics, and it flows directly from quantum mechanics and the mathematics of spin. Meanwhile, A young British physicist named Paul Dirac was working on something that would push quantum mechanics into entirely new territory. Dirac was extraordinary, quiet, precise, almost unnervingly logical. He spoke in complete, perfectly formed sentences and was famously literal. There's a story, probably apocryphal but telling, that when someone at a lecture said, "I don't understand the equation on the top right of the blackboard," Dirac simply replied, "That is a statement, not a question." He thought in mathematics the way most people think in words, and in 1928, at the age of 25, he did something remarkable. He set out to write a version of quantum mechanics that was compatible with Einstein's special relativity. Schrödinger's equation worked beautifully, but it wasn't relativistic. It didn't account for the fact that particles can move at speeds close to the speed of light, where the rules of special relativity become important. Dirac wanted an equation that combined quantum mechanics and special relativity into a single, consistent framework. And when he found it, the Dirac equation, it was elegant in a way that took everyone's breath away. It was compact, it was beautiful, and it was strange. The equation fit on a single line, and yet packed inside it were consequences no one had anticipated. Consequences that would reshape physics. Let me try to give you a sense of what Dirac found. He wasn't just bolting relativity onto quantum mechanics like an afterthought. He derived his equation from first principles, insisting that it respect both the rules of quantum mechanics and the symmetry requirements of special relativity. And when he wrote it down, something unexpected fell out of the mathematics. The equation naturally, automatically, without being asked, predicted that electrons must have spin. Remember how Uhlenbeck and Gaudsmit had proposed electron spin in 1925 as a kind of ad hoc addition? This mysterious intrinsic angular momentum that didn't correspond to anything actually spinning. They'd grafted it onto the existing theory because the experiments demanded it. But Dirac's equation didn't need spin grafted on. Spin emerged from the mathematics itself as a necessary consequence of combining quantum mechanics with relativity. That's extraordinary. It meant spin wasn't some weird add-on or a quirk of electrons. It was a deep feature of the universe, woven into the very fabric of how quantum mechanics and relativity fit together. And the equation got the value exactly right. Spin 1/2, precisely what the experiments showed. But here's where it gets really wild. The Dirac equation had solutions that nobody knew what to do with. When you solved it, you got the expected solutions describing electrons with positive energy. But you also got solutions with negative energy. Lots of them. An infinite sea of negative energy, states stretching downward without limit. Now, in classical physics, you might just ignore these, say they're unphysical, toss them out. But in quantum mechanics, you can't do that so easily. If those negative energy states exist, then an ordinary electron should be able to radiate energy and drop down into one of them, and then drop further and further. Every electron in the universe should cascade down into these negative energy states, releasing infinite energy in the process. Obviously, that doesn't happen. So what's going on? Dirac thought about this for a while, about a year actually, and in 1930, he proposed something audacious. He suggested that all those negative energy states are already filled, every single one of them. The entire infinite sea of negative energy states is occupied by electrons, and because electrons are fermions obeying Pauli's exclusion principle, no more electrons can fall into those states. They're taken. The vacuum of empty space, in Dirac's picture, isn't really empty at all. It's a vast, invisible ocean of negative energy electrons, and we simply don't notice them because they're uniform and everywhere, like water to a fish. And then Dirac took the next logical step, which is where this becomes genuinely prophetic. He reasoned that if you pumped enough energy into this sea, if a high-energy photon, say, knocked one of those negative energy electrons up into a positive energy state, you'd see two things happen. You'd see an ordinary electron appear, and you'd also see a hole left behind in the negative energy sea. That hole, that absence of a negative energy, negatively charged electron, would look like a particle with positive energy and positive charge. It would look like a positively charged electron. Dirac had predicted antimatter. He was initially cautious about this. In 1930, the only known positively charged particle was the proton, and Dirac at first wondered if the holes might somehow be protons. But the math was clear. The hole had to have the same mass as the electron, and protons are nearly 2,000 times heavier. Other physicists, including Robert Oppenheimer and Hermann Weyl, pointed this out, and Dirac eventually accepted it. There had to be a new particle out there, an anti-electron, identical to the electron in every way except carrying a positive charge. And then, in 1932, the American physicist Carl Anderson found it. Anderson was studying cosmic rays at Caltech using a cloud chamber, a device where charged particles leave visible trails of condensation as they pass through supersaturated vapor. He placed his cloud chamber in a strong magnetic field which curves the paths of charged particles, positive charges curving one way, negative charges curving the other. And he kept seeing tracks that curved the wrong way. They looked like electron tracks, same mass, same ionization pattern, but they curved as if they carried a positive charge. Anderson called the particle a positron, and it was exactly what Dirac's equation had predicted. Anderson won the Nobel Prize in 1936 for the discovery, and Dirac had already shared the 1933 Nobel with Schrödinger. Think about what happened here. A 25-year-old sat down with a pencil and demanded that quantum mechanics and relativity be mathematically consistent. The equation he wrote down told him that a particle no one had ever seen must exist. And a few years later, someone found it in a cloud chamber on a rooftop in Pasadena. That's the power of mathematical physics at its deepest. The universe, somehow, was already obeying Dirac's equation before Dirac ever wrote it down. The discovery of antimatter opened up an entirely new way of thinking about the physical world. Every particle, it turned out, has an antiparticle. Not just electrons. Protons have antiprotons. Neutrons have antineutrons. When a particle meets its antiparticle, they annihilate each other, converting their combined mass entirely into energy via Einstein's E equals mc squared. And the reverse can happen too. Enough concentrated energy can spontaneously produce a particle-antiparticle pair out of nothing. This is real, by the way. It happens in particle accelerators every day. It happens in your body, if you've ever had a PET scan, positron emission tomography. The positron in PET is Dirac's anti-electron, produced by radioactive decay and annihilating with electrons in your tissue to produce the gamma rays that the scanner detects. Antimatter isn't science fiction, it's medical imaging. But let's step back from the fireworks for a moment and settle into something quieter, because while Dirac was rewriting the rules of particles, the philosophical battle over quantum mechanics was still raging. And in 1935, Einstein made what he considered his strongest move. By this point, Einstein had largely stopped trying to prove quantum mechanics was wrong in the sense of giving incorrect predictions. He accepted that the theory worked. It predicted experimental results with stunning accuracy. But he believed it was incomplete. He believed there was a deeper reality underneath, a layer of hidden variables that quantum mechanics simply couldn't see. The randomness, the uncertainty, the probability. In Einstein's view, these weren't features of nature itself, but symptoms of our ignorance, like the statistical mechanics of gas molecules. The individual molecules have definite positions and velocities. We just don't track them all, so we use probabilities. Einstein wanted quantum mechanics to be like that, a useful statistical tool built on top of a deterministic reality. In May 1935, Einstein, along with two younger colleagues at the Institute for Advanced Study in Princeton, Boris Podolsky and Nathan Rosen, published a paper that would become one of the most discussed papers in the history of physics. It's known as the EPR paper, after their initials, and its title asked a pointed question. Can quantum mechanical description of physical reality be considered complete? Their argument was clever, and it introduced an idea that would haunt physics for decades. Here's the setup. Quantum mechanics predicts that certain pairs of particles can be created in what we now call an entangled state. Imagine two particles flying apart from a common source in opposite directions. Quantum mechanics says that certain properties of these particles, say their spin, are correlated in a very specific way. If you measure one particle and find its spin pointing up, you instantly know the other particle's spin is pointing down, no matter how far apart they are. That much isn't necessarily strange. You could imagine the spins were determined at the moment of creation, like putting one red ball and one blue ball into separate boxes and shipping them to opposite sides of the world. Opening one box tells you what's in the other. No mystery. But quantum mechanics says something more radical than that. It says the particles don't have definite spin values until you measure one of them. Before measurement, each particle is in a superposition of spin up and spin down. The act of measuring one particle doesn't just reveal its spin. It determines it, and simultaneously determines the spin of the distant partner. Einstein found this deeply troubling. He called it spooky action at a distance. How could measuring a particle here instantaneously affect a particle light years away? That would seem to violate the spirit, if not the letter, of relativity, which says nothing, no signal, no influence, can travel faster than light. The EPR argument was essentially this. Either quantum mechanics is incomplete, and the particles really do have definite properties all along, determined by hidden variables we haven't discovered yet, or measuring one particle really does instantaneously influence the other, which would mean the theory allows some kind of non-local connection that seems physically unreasonable. Einstein, Podolsky, and Rosen concluded that quantum mechanics must be incomplete. There must be hidden variables. Bohr responded almost immediately, publishing a rebuttal in the same journal with the same title. Bohr's response was, characteristically, dense and philosophical. He argued that you couldn't separate the properties of the particles from the measurement context, that asking about the spin of a particle independent of how you chose to measure it was meaningless within quantum mechanics. The EPR argument, Bohr said, was based on an assumption about physical reality that quantum mechanics simply didn't support. Most physicists at the time sided with Bohr, or at least moved on. The EPR argument seemed philosophical rather than practical. You couldn't design an experiment to distinguish between the two positions, or so everyone thought. Einstein and Bohr would continue their disagreement for the rest of their lives. Einstein died in 1955, Bohr in 1962, and neither budged. But the EPR paper planted a seed. It raised a question that was precise enough, specific enough, that eventually, decades later, someone would figure out how to actually test it. And that someone was an Irish physicist named John Stuart Bell, working at CERN in Geneva in the early 1960s. Bell was one of those rare physicists who took the foundational questions seriously at a time when most of his colleagues considered them settled or irrelevant. The prevailing attitude in physics departments was sometimes called, "Shut up and calculate. The theory works. It gives correct predictions. Stop worrying about what it means." Bell didn't accept that. In 1964, Bell published a short, elegant paper that changed everything. He proved a mathematical theorem, now called Bell's theorem, that drew a sharp, testable line between quantum mechanics and any possible hidden variable theory of the type Einstein had envisioned. What Bell showed was that if hidden variables exist and if the universe respects locality, meaning no instantaneous influences between distant particles, then the correlations you'd measure between entangled particles are bounded. They can only be so strong. He expressed this as a mathematical inequality, now called a Bell inequality. And here's the kicker. Quantum mechanics predicts correlations that violate that inequality. Quantum mechanics predicts that entangled particles are more correlated than any local hidden variable theory could possibly allow. This was no longer philosophy. This was a concrete, experimental prediction. You could actually build an apparatus, create entangled particles, measure their correlations, and check whether the Bell inequality was satisfied or violated. If it was satisfied, Einstein was right and quantum mechanics was incomplete. If it was violated, then either hidden variables don't exist, or the universe is non-local in some deep and fundamental way, or both. Either way, something profound was at stake. The first serious, experimental tests came in the 1970s, with John Clauser and Stuart Friedman at Berkeley performing a version of the experiment in 1972. Their results favored quantum mechanics. The Bell inequality was violated. But the experiment had loopholes, technical gaps that a determined skeptic could point to. Maybe the detectors weren't efficient enough. Maybe the measurement settings were determined in advance, allowing some subtle classical explanation to sneak in. And so the stage was set for a more definitive test, and the person who would carry it out was a young French physicist named Alain Aspect, working at the University of Paris-Sud in Orsay. In the early 1980s, Aspect designed a series of experiments that were more rigorous, more carefully controlled, and that addressed the most important loopholes. His key innovation was to switch the measurement settings while the photons were already in flight. Think about why that matters. In the Clauser-Friedman experiment, the polarizer orientations were fixed before the experiment began. A stubborn skeptic could argue, well, maybe the particles somehow knew in advance what measurements they'd face and adjusted their behavior accordingly. It sounds far-fetched, but if you're trying to close every possible door to a classical explanation, you have to take it seriously. Aspect's apparatus used rapid acousto-optical switches, devices that could redirect each photon to one of two differently oriented polarizers, and these switches operated so fast that the choice of measurement setting was made after the entangled photons had already been emitted and were racing toward opposite ends of the lab. The switching happened in nanoseconds, far too quickly for any signal traveling at the speed of light to carry information from one detector to the other. So even if you imagined some hidden communication between the particles, some secret handshake happening at light speed, it couldn't have arrived in time to influence the result. The particles were, for all practical purposes, making their choices in total isolation from each other. And the results? The Bell inequality was violated decisively. The correlations aspect measured matched the predictions of quantum mechanics almost perfectly. This was 1982, and while there were still some remaining loopholes, there always are in any real experiment, the result landed with enormous weight. The physics community took notice. The universe, it seemed, really was as strange as quantum mechanics said it was. Entangled particles really do exhibit correlations that no local hidden variable theory can explain. Einstein's dream of a deeper, more sensible layer underneath quantum mechanics, at least the local realistic version of that dream, was looking increasingly untenable. Now, I want to pause here and make sure something is clear, because this is a point that gets muddled a lot in popular accounts. When we say the Bell inequality is violated, when we say entangled particles are correlated in this spooky way, we are not saying that information travels faster than light. That's a really important distinction. You cannot use entanglement to send a message. Here's why. When you measure your entangled photon, you get a random result. Say, polarization up or polarization down. It's genuinely random. You can't control which outcome you get. Your distant partner measuring their photon also gets a random result. It's only when you later compare your results, which requires ordinary, slower-than-light communication, that you discover the correlations. The magic is in the pattern, not in any individual measurement. So relativity is safe. No faster-than-light telegrams. But the correlations themselves are real, and they're stronger than anything classical physics can account for. That's what Bell proved, and that's what aspect confirmed. The story doesn't end there, of course. Over the following decades, experimenters kept tightening the screws, closing one loophole after another. In 2015, a team at Delft University of Technology in the Netherlands, led by Ronald Hansen, performed what's often called the first loophole-free Bell test. They used entangled electrons separated by over a kilometer, with measurement settings determined by random number generators and detectors efficient enough to close the so-called detection loophole. The result? Violation of the Bell inequality again. Quantum mechanics again. And in 2022, the Nobel Prize in Physics was awarded jointly to John Clauser, Alain Aspect, and Anton Zeilinger. Zeilinger being an Austrian physicist who had done groundbreaking work on quantum teleportation and entanglement-based technologies for their experiments establishing the violation of Bell inequalities and pioneering quantum information science. It was a moment of recognition, not just for three individuals, but for a question that had been simmering since 1935, when Einstein, Podolsky, and Rosen first asked whether quantum mechanics could really be the whole story. So let's sit with that for a moment. By the mid-1980s, the experimental verdict was in, at least provisionally. Quantum mechanics was not incomplete in the way Einstein had hoped. There were no local hidden variables pulling strings behind the curtain. The randomness was real. The entanglement was real. And the universe was, at its most fundamental level, stranger than any classical intuition could accommodate. But here's what's fascinating. This wasn't the end of the debate about interpretation. If anything, the confirmation of Bell inequality violations opened up new questions. If the universe isn't locally realistic, then what is it? Which assumption fails? Locality, realism, or both? And different answers to that question lead to genuinely different pictures of reality. The Copenhagen interpretation, which had been the dominant framework since the late 1920s, essentially says, don't worry about what's really happening between measurements. The wave function is a tool for calculating probabilities, and when you measure, you get a definite result. That's all you can say. It's pragmatic, almost aggressively so. And for decades, it worked beautifully. Most physicists adopted it, did their calculations, got their predictions, and moved on. But not everyone was satisfied. And by the latter half of the 20th century, alternative interpretations started gaining serious traction. One of the most striking is the many worlds interpretation, proposed by Hugh Everett III in his 1957 doctoral dissertation at Princeton. Everett was a fascinating character, a brilliant, somewhat reclusive thinker who wrote his thesis under John Wheeler, one of the towering figures of 20th century physics. Everett's idea was radical. He said, what if the wave function never collapses? What if, instead, every time a quantum measurement is made, the universe splits into branches, one branch for each possible outcome, and all of them are equally real? You measure a photon's polarization and get up. In another branch of reality, another version of you got down. Both outcomes happen. Both are real. You just only experience one branch. It sounds like science fiction, and when Everett first proposed it, the idea was largely ignored. Niels Bohr's circle was unimpressed. Everett himself eventually left academia, went into defense analysis and computing, and never returned to physics. He died in 1982, at just 51. But his idea refused to die with him. Starting in the 1970s and accelerating through the 1980s and 1990s, many worlds gained a growing following among physicists and philosophers. Bryce DeWitt, a physicist at the University of North Carolina, championed the interpretation and gave it the name many worlds, which Everett himself hadn't used. And today, if you poll physicists, which people actually have done, many worlds is one of the most popular interpretations, neck and neck with Copenhagen in some surveys. It's not fringe. It's a serious contender. But here's the thing about interpretations, and this is important to understand. They all agree on the math. They all use the same equations, the same Schrödinger equation, the same rules for calculating probabilities. They disagree about what the math means. Copenhagen says the wave function is a calculational tool. Many worlds says it's a literal description of a branching multiverse. Another interpretation, the pilot wave theory developed by David Bohm in 1952, says particles do have definite positions at all times. There are hidden variables. But they're guided by a wave that is explicitly non-local, meaning it connects distant parts of the universe in exactly the way Einstein found distasteful. Bohm's theory reproduces all the predictions of standard quantum mechanics, but it does so at the cost of accepting non-locality as a fundamental feature of reality. It's deterministic, which Einstein would have liked, but it's non-local, which he wouldn't have. You can't have everything, it seems. And then there are more recent approaches. Decoherence theory, which explains how quantum superpositions appear to collapse through interaction with the environment, without needing a special collapse postulate. The idea, developed extensively by physicists like H. Dieter Zeh and Wojciech Zurek, starting in the 1970s and 1980s, is that when a quantum system interacts with a large number of environmental particles, air molecules, photons, whatever, the different branches of its wave function become entangled with the environment in a way that makes them effectively invisible to each other. The interference effects that make quantum mechanics so weird get washed out, diluted into the vast complexity of the environment. The system looks classical, not because the wave function has collapsed, but because the quantum coherence has leaked away into the surroundings. It's an elegant idea, and it's become an essential part of how physicists think about the quantum to classical transition. But it doesn't fully resolve the measurement problem. It explains why you don't see superpositions in everyday life, but it doesn't quite tell you why you experience one particular outcome rather than another. So, here we are, deep into the 20th century, and quantum mechanics is arguably the most successful theory in the history of science. Its predictions have been confirmed to extraordinary precision. The magnetic moment of the electron, for instance, has been measured and calculated to agree to better than 1 part in a trillion. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. And yet, the people who use this theory every day still can't agree on what it means. That's a remarkable situation. It's as if you had a map that was perfectly accurate, that never led you astray, but nobody could agree on what kind of territory it was describing. And while the philosophers and the theorists debated meaning, the engineers and the experimentalists were busy doing something else entirely. They were putting quantum mechanics to work. Because starting in the mid-20th century, quantum physics stopped being just a theory about atoms and started becoming the foundation of an entire technological civilization. And the story of how that happened, how the strange, counterintuitive physics of the very small became the engine driving the modern world, begins in many ways with a material that nobody thought was particularly interesting. A material that sits right in the middle of the periodic table's electrical conductivity range, neither a good conductor nor a good insulator, a semiconductor. And the one that would change everything was silicon, element 14, the second most abundant element in the Earth's crust, hiding in plain sight in every grain of sand on every beach you've ever walked on. The question was whether anyone could figure out how to make it do something useful. Because in its raw, natural state, silicon is interesting, but not exactly cooperative. It forms crystals, sure, beautiful, orderly lattices where every silicon atom bonds to 4 neighbors in a perfect tetrahedral arrangement. But electrically, it just kind of sits there. At room temperature, pure silicon barely conducts at all. Not enough free electrons bouncing around to carry a meaningful current. And that's where quantum mechanics enters the picture. Because the reason silicon behaves the way it does, the reason any solid behaves the way it does, comes down to something called band theory. And band theory is quantum mechanics applied to the collective behavior of electrons in a crystal. Here's the idea. When you have a single atom, its electrons occupy discrete energy levels. Those quantized orbits we talked about way back with Bohr, and then refined with Schrödinger's wave equation. But when you pack billions upon billions of atoms together into a crystal lattice, something remarkable happens. Those individual energy levels don't just stay the same. They spread out. They smear into bands, continuous ranges of energy that electrons are allowed to occupy. And between those bands, there are gaps, forbidden zones where no electron can exist, no matter what. The size of that gap, the band gap, turns out to determine almost everything about a material's electrical behavior. In a metal like copper, the highest occupied band overlaps with the next empty band, so there's essentially no gap at all. Electrons can freely jump to slightly higher energy states, which means they can move through the material easily when you apply a voltage. That's why metals conduct so well. In an insulator like diamond, the band gap is enormous, around 5.5 electron volts. Electrons in the lower band would need a huge kick of energy to jump across that gap into the conduction band, so under normal conditions, they just stay put. No mobile electrons, no current, no conduction. But silicon? Silicon sits right in that sweet spot. Its band gap is about 1.1 electron volts. Not too big, not too small. At absolute zero, pure silicon would be a perfect insulator, every electron locked in place. But at room temperature, there's just enough thermal energy that a small number of electrons can hop across that gap into the conduction band, leaving behind what physicists call holes, empty spots in the lower band that behave almost like positively charged particles moving in the opposite direction. So silicon conducts a little, but not a lot. A semiconductor, right there in the name. Now, here's where it gets clever. The real breakthrough wasn't just understanding silicon's natural properties, it was learning how to manipulate them. And the technique is called doping, which is a wonderfully straightforward name for a wonderfully elegant process. You take your pure silicon crystal and you deliberately introduce tiny amounts of impurity atoms. Not much. Maybe 1 impurity atom for every million silicon atoms. But that tiny contamination changes everything. If you add atoms that have 5 outer electrons instead of silicon's 4, phosphorus is the classic example, then 4 of those electrons bond happily with the surrounding silicon atoms, but the 5th one has nowhere to go. It's loosely bound, barely attached, and at room temperature it breaks free almost immediately, becoming a mobile charge carrier. You've just created N-type silicon, N for negative, because you've added extra electrons. Alternatively, if you dope with atoms that have only 3 outer electrons, boron typically, then there's a missing bond, a hole, and that hole can migrate through the lattice as neighboring electrons shuffle over to fill it. That gives you P-type silicon, P for positive. And this is all quantum mechanics. The band structure, the energy gaps, the behavior of dopant atoms, the statistics governing how electrons distribute themselves across energy levels. All of it comes straight from Schrödinger's equation and the Pauli exclusion principle and Fermi-Dirac statistics. Every bit of it. Without quantum mechanics, you couldn't predict any of this. You couldn't design any of this. You'd be fumbling in the dark. The real magic happens when you put N-type and P-type silicon together. Right at the junction, the p-n junction, electrons from the N side diffuse across and fill holes on the P side, creating a thin region depleted of free carriers. This depletion zone acts like a one-way valve for current. Apply voltage one way, and current flows easily. Reverse it, and the junction blocks the flow. You've just made a diode, the simplest semiconductor device, and it's the ancestor of essentially every electronic component in the modern world. The transistor, though, that was the real revolution. December 1947, Bell Laboratories in Murray Hill, New Jersey. John Bardeen and Walter Bratton, working under William Shockley's group, demonstrated the first point-contact transistor. It was a crude little thing. A slab of germanium, actually, not silicon, with 2 gold contacts pressed close together on its surface, held in place by a plastic wedge glued to a spring. It looked almost comically primitive. But when they applied a small signal to one contact, it controlled a much larger current flowing through the other. Amplification. A tiny whisper of input producing a shout of output. They'd achieved what vacuum tubes had been doing for decades, but in a device that was smaller, cooler, more reliable, and used a fraction of the energy. The human dynamics behind this invention were, honestly, messy. Shockley had originally conceived of a different type of transistor, a field effect design, but couldn't get it to work. Bardeen, a quiet, brilliant theorist, figured out why. Surface states were trapping the electrons and screening the electric field. That theoretical insight unlocked the path forward, and Brattain, a gifted experimentalist, built the device that proved it. When the Nobel Prize came in 1956, all three shared it, but Shockley was furious that he hadn't been the one to actually build the first working transistor. His ego, always considerable, metastasized. He left Bell Labs, moved to Palo Alto, California, and founded Shockley Semiconductor Laboratory in 1956, hiring the best young minds he could find. But he was such a difficult, paranoid, abrasive manager that within a year, 8 of his top researchers, the so-called traitorous 8, walked out and founded Fairchild Semiconductor. And from Fairchild would eventually spin out Intel, AMD, and dozens of other companies. The entire Silicon Valley ecosystem traces its lineage back to a brilliant, impossible man that nobody could work with. There's a lesson in there somewhere. But anyway, the point is that the transistor changed everything. And the key step, the step that turned transistors from individual components soldered onto circuit boards into the foundation of modern computing, was integration. In 1958, Jack Kilby at Texas Instruments demonstrated the first integrated circuit. Multiple transistors and other components fabricated on a single piece of semiconductor material. Around the same time, Robert Noyce at Fairchild independently developed a more practical version using planar technology and silicon instead of germanium. Their approaches were different enough that both are credited as co-inventors, and the patent disputes took years to sort out. But the concept was transformative. Instead of wiring together hundreds of individual transistors by hand, you could photograph a circuit design onto a silicon wafer and etch the entire thing at once. Thousands of components, then millions, then billions, all on a chip the size of your fingernail. And here's what's really wild about this. Every single one of those billions of transistors works because of quantum mechanics. The band gaps, the doping profiles, the tunneling currents, the oxide layer thicknesses, all of it is quantum mechanical. When engineers at Intel or TSMC design a chip with transistors whose gate lengths are 3 nanometers, 3 billionths of a meter, maybe 15 atoms across, they're not working in a regime where classical physics offers any useful guidance at all. At those scales, electrons are wave functions. Tunneling is a constant concern. The Heisenberg uncertainty principle isn't an abstract philosophical curiosity. It's an engineering constraint that determines whether your chip works or overheats or simply fails. Quantum mechanics isn't lurking in the background of modern electronics. It's the entire foundation. And it doesn't stop at computing. Think about lasers. Theodore Maiman built the first working laser in 1960, using a synthetic ruby crystal and a flash lamp, and the entire principle behind it, stimulated emission, was predicted by Einstein back in 1917. When an atom in an excited state encounters a photon with exactly the right energy, it can be stimulated to emit an identical photon, same wavelength, same phase, same direction. 1 photon becomes 2, 2 become 4, and if you put mirrors at both ends to bounce the light back and forth through the gain medium, you get an avalanche of perfectly coherent light. That's a laser. And lasers are everywhere now. Fiber optic communications, barcode scanners, eye surgery, laser cutting, the little red dot from a presentation pointer. Every one of them is stimulated emission, which is quantum mechanics. Or think about LEDs, light-emitting diodes. When an electron in a semiconductor falls from the conduction band back down across the band gap and recombines with a hole, it can release that energy as a photon. The color of the light depends on the size of the band gap. Smaller gaps give you infrared or red. Larger gaps give you blue or ultraviolet. For decades, engineers could make red and green LEDs easily enough, but blue was elusive because it required materials with wider band gaps that were incredibly difficult to grow as quality crystals. It took Shuji Nakamura, working largely alone at a small Japanese chemical company called Nichia in the early 1990s, to crack the problem using gallium nitride. His colleagues thought he was wasting his time. His employer nearly pulled his funding more than once, but he figured out how to grow high-quality gallium nitride crystals and created the first bright blue LED. That earned him a share of the 2014 Nobel Prize in Physics, and it also gave the world white LED lighting, because once you have blue, you can coat it with a phosphor that converts some of the blue light to yellow, and the combination looks white to your eyes. Today, LED lighting saves an almost incomprehensible amount of energy worldwide. Billions of dollars, millions of tons of carbon emissions, all because one stubborn engineer refused to give up on a quantum mechanical process in a crystal that nobody else believed in. And there's another quantum technology that you've almost certainly used without thinking about it, one that sounds almost like science fiction when you first hear about it. It lives inside every smartphone, every digital camera, every telescope that captures images of distant galaxies. It's called a charge-coupled device, a CCD, and it works because of the photoelectric effect, that same phenomenon Einstein explained in 1905, the one that first introduced the idea of light quanta. Photons strike a silicon surface, knock electrons free, and those electrons are collected, counted, and turned into a digital image. Every photograph you've ever taken with a phone is, at its most fundamental level, Einstein's photoelectric effect happening millions of times across millions of tiny pixel sensors. The quantum revolution isn't something that happened in a lab somewhere and stayed there. It crawled into every corner of daily life, so quietly that most people never even noticed. And yet, for all of these extraordinary applications, transistors, lasers, LEDs, solar cells, MRI machines, the atomic clocks that keep GPS satellites synchronized to within billionths of a second, there was always a sense, especially from the late 1990s onward, that quantum mechanics had another trick up its sleeve, something that went beyond simply exploiting quantum effects in bulk materials, something that used the full strangeness of superposition and entanglement not as obstacles to be managed, but as resources to be harnessed. And that idea, the idea that you could build a computer that doesn't just benefit from quantum mechanics but actually computes using quantum mechanical principles, had been floating around in various forms since at least 1981, when Richard Feynman stood up at a conference at MIT and made an observation that seemed so simple, so obvious in hindsight, and yet so profound that it essentially launched an entirely new field. What Feynman pointed out was this: if you want to simulate a quantum system, say a molecule with 50 or 100 atoms, each with electrons in superposition, each entangled with its neighbors, the amount of information you need to track grows exponentially, not linearly, not even polynomially, but exponentially. Every additional quantum particle doubles the amount of classical information required to describe the system. A system of 10 quantum particles needs you to track roughly 1,000 numbers. 20 particles, about 1,000,000. 30 particles, 1,000,000,000. By the time you get to maybe 300 interacting quantum particles, you'd need more numbers than there are atoms in the observable universe. No classical computer, no matter how fast, no matter how much memory you gave it, could ever hope to simulate that system in any reasonable amount of time. And Feynman, being Feynman, didn't just point out the problem and sit down. He suggested the solution. If nature computes quantum mechanics so effortlessly, If every molecule in your body is solving these impossibly complex quantum equations in real time just by existing, then maybe the way to simulate quantum systems is to build a computer that itself runs on quantum mechanical principles. A quantum computer. Fight fire with fire, in a sense. Use quantum weirdness to compute quantum weirdness. Now, at the time, in 1981, this was a beautiful idea with absolutely no practical path to realization. It was a thought experiment, a provocation. Feynman wasn't handing anyone a blueprint. He was saying, look, there's something fundamentally important here, and someone should figure out how to do it. And for about a decade, the idea mostly lived in the realm of theoretical physics and computer science, kicked around by a small community of people who found it fascinating but didn't quite know what to do with it. The first major breakthrough in making quantum computing seem like more than a dream came in 1994 from a mathematician at Bell Labs named Peter Shor. And here's where the story gets really interesting, because Shor didn't just prove that a quantum computer could do something faster than a classical computer. He proved it could do something that would shake the foundations of modern security. Shor developed an algorithm, now called Shor's algorithm, that could factor large numbers exponentially faster than any known classical algorithm. And you might think, okay, factoring numbers, that sounds like a math homework problem. Who cares? But here's the thing. Almost all of the encryption that protects your bank transactions, your emails, your medical records, the entire infrastructure of internet security, it relies on the assumption that factoring very large numbers is practically impossible for classical computers. The RSA encryption scheme, which has been a backbone of digital security since the late 1970s, works precisely because if you multiply two large prime numbers together, it's easy to get the product, but going backward, figuring out which two primes produce that product, is astronomically hard for a classical machine. A number with a few hundred digits could take all the classical computers on Earth longer than the age of the universe to factor. Shor showed that a sufficiently powerful quantum computer could do it in hours, maybe minutes. The implications were staggering. Overnight, quantum computing went from an obscure theoretical curiosity to a matter of national security. Governments started paying attention, funding started flowing, and the race was on. But building an actual quantum computer, that turned out to be one of the hardest engineering challenges humans have ever attempted. And to understand why, you need to understand what makes a quantum computer fundamentally different from a classical one, and why that difference is both its superpower and its Achilles heel. In a classical computer, information is stored in bits. Each bit is either a 0 or a 1. That's it. Every computation your laptop performs, every video it streams, every email it sends, is ultimately just an enormous sequence of zeros and ones being shuffled around according to logical rules. A quantum computer replaces the classical bit with something called a qubit, a quantum bit. And a qubit can be a 0 or a 1 or, and this is the key, a superposition of both simultaneously. Think back to everything we talked about earlier, all those hours ago, about superposition and how a quantum particle doesn't have a definite state until it's measured. A qubit exploits exactly that. Before you measure it, it exists in a blend of 0 and 1, described by probability amplitudes, those complex numbers that Schrödinger's equation tracks so beautifully. Now, one qubit in superposition isn't that impressive on its own. But here's what's wild. When you have two qubits, they can be entangled. Remember entanglement? that strange correlation that Einstein called spooky action at a distance, the one that Aspect and Clauser and Zeilinger won the Nobel Prize for confirming? When qubits are entangled, the state of one is fundamentally linked to the state of the others, and the system as a whole exists in a superposition of all possible combinations. 2 qubits can represent 4 states simultaneously, 3 qubits, 8 states, 10 qubits over 1,000, 50 qubits over a quadrillion. The computational space grows exponentially with each qubit you add. That's the same exponential scaling that makes quantum systems impossible for classical computers to simulate. But now you're harnessing it, turning it into computational power rather than computational obstacle. The trick, though, and this is where the engineering becomes almost impossibly difficult, is that qubits are extraordinarily fragile. Superposition and entanglement are delicate quantum states that collapse at the slightest disturbance. A stray photon, a tiny vibration, a fluctuation in temperature. Any of these can cause what's called decoherence, where the qubit loses its quantum properties and behaves like an ordinary classical bit. It's like trying to balance a coin on its edge on the deck of a ship in a storm. The quantum information just leaks away into the environment. This is why most quantum computers today operate at temperatures colder than outer space. The superconducting qubit systems built by companies like IBM and Google are cooled to about 15 millikelvin. That's 15,000ths of a degree above absolute zero, colder than the cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space at about 2.7 Kelvin. These machines use elaborate refrigeration systems called dilution refrigerators, towering gold-plated structures that look like chandeliers from some science fiction cathedral. And even at those extreme temperatures, even with all that shielding and isolation, qubits still decohere. The longest-lived superconducting qubits today maintain their quantum states for maybe a few hundred microseconds. That's a few hundred millionths of a second. Every computation has to happen within that tiny window before the quantum information dissolves. So there's been this enormous effort, spanning decades now, to figure out how to make qubits last longer, how to correct errors when they inevitably occur, and how to scale up from a handful of qubits to the thousands or millions that would be needed for truly transformative computations, like running Shor's algorithm on real-world encryption keys. Quantum error correction is itself a deep and beautiful field. The basic idea is that you spread a single logical qubit's worth of information across many physical qubits, so that even when individual qubits decohere or pick up errors, the overall quantum information is preserved. But the overhead is significant. Current estimates suggest you might need something like 1,000 physical qubits to create one reliable logical qubit. So a useful quantum computer might need millions of physical qubits, and right now, the largest machines have on the order of 1,000 or so. In 2019, Google made headlines by claiming what they called quantum supremacy, or quantum advantage, as some prefer to call it. Their 53-qubit processor, called Sycamore, performed a specific calculation in about 200 seconds that Google estimated would take the most powerful classical supercomputer roughly 10,000 years. IBM pushed back on that claim, arguing that with clever classical techniques, the supercomputer could do it in a matter of days, not millennia. The debate continues, and it highlights something important about where we are in the quantum computing story. We're at the very beginning. Think of it like the early days of classical computing, the ENIAC era, the late 1940s, when computers filled entire rooms and could barely do what a pocket calculator does today. Nobody back then could have predicted smartphones, the internet, artificial intelligence, We're at that same threshold with quantum computing. The machines exist. They work. They can do things that are genuinely hard for classical computers, but they're noisy, error-prone, and limited in scale. And yet, the potential applications are breathtaking. Beyond cryptography, quantum computers could revolutionize drug discovery by accurately simulating molecular interactions. Exactly the kind of quantum simulation Feynman originally envisioned. They could optimize complex systems like supply chains, financial portfolios, air traffic routing. They could accelerate machine learning in ways we don't fully understand yet. They could help design new materials, better batteries, better superconductors, better catalysts for pulling carbon dioxide out of the atmosphere. Every one of these applications comes down to the same fundamental advantage. Quantum computers can explore vast spaces of possibilities simultaneously in ways that classical computers, plodding through one possibility at a time, simply cannot match. And here's something worth sitting with for a moment, something that brings this whole long story full circle. The quantum mechanics that makes all of this possible, the superposition, the entanglement, the probability amplitudes, the uncertainty. It's the same physics that Planck stumbled into reluctantly in 1900, trying to fix a formula for how hot objects glow. It's the same physics that Einstein used to explain the photoelectric effect in 1905, the same physics that Bohr used to save the atom in 1913, the same physics that Heisenberg and Schrödinger wrestled into mathematical form in the mid-1920s. The same physics that Einstein spent the last 30 years of his life arguing couldn't possibly be the complete story. Every transistor in the device you're listening to right now, every photon from the LED illuminating your room, every GPS signal that guided you home today, all of it flows from those first tentative steps into the quantum world, taken by people who often didn't fully understand or even accept what they were discovering. That's maybe the most remarkable thing about this whole story. Quantum mechanics was never intuitive. It was never comfortable. From the very beginning, it disturbed the people who created it. Planck called his own quantum hypothesis an act of desperation. Einstein, who did as much as anyone to establish quantum theory, never made peace with its implications. Schrödinger devised his famous cat thought experiment specifically to show how absurd the theory seemed. Bohr spent decades defending an interpretation that even he admitted defied ordinary understanding. And yet, every single prediction quantum mechanics has ever made has been confirmed by experiment. Every single one. To a precision that is, frankly, almost unreasonable. The magnetic moment of the electron, predicted by quantum electrodynamics and measured in the laboratory, agrees to better than 10 parts per billion. It's the most accurate prediction in the history of science. So here you are, lying in the dark, and the universe around you is humming with quantum mechanics. The electrons in every atom of your body are obeying Schrödinger's equation right now, their positions smeared out in probability clouds, their spins entangled with neighboring particles in ways too complex for any classical description. The photons from your screen or your speaker are quantized packets of electromagnetic energy, just as Einstein described them over a century ago. The nuclear reactions in the sun that produced the energy that grew the food that powers your brain. Those reactions depend on quantum tunneling, particles passing through barriers they classically shouldn't be able to cross. Without quantum mechanics, the sun wouldn't shine. Without quantum mechanics, chemistry wouldn't work. Without quantum mechanics, you wouldn't exist. And the story isn't over. It's not even close to over. Quantum gravity remains one of the great unsolved problems in physics. How do you reconcile quantum mechanics with Einstein's general relativity, the theory that describes gravity as the curvature of space-time? Nobody knows yet. Quantum computing is still in its infancy, full of promise and unsolved engineering challenges. The foundations of quantum mechanics. What it really means, what's actually happening when a particle is in superposition, whether there are many worlds or pilot waves or something nobody has thought of yet. These questions are still open, still debated, still capable of surprising us. But for tonight, let that all drift. Let the equations and the experiments and the names and the dates settle like snow. Planck and his reluctant quanta, Einstein and his stubborn photons, Bohr and his orbiting electrons, Heisenberg and his matrices, Schrödinger and his waves, Dirac and his beautiful equation that predicted a mirror universe of antimatter, Bell and his inequality, Aspect and his entangled photons. All of those people, across more than a century, each adding a piece to this extraordinary, counterintuitive, endlessly surprising picture of reality. They didn't always agree with each other. They didn't always understand what they'd found. But together, step by step, argument by argument, experiment by experiment, they uncovered something true about the universe, something strange and deep and beautiful. And now you know the story, or at least enough of it to dream about. So let it carry you. Let the quantum world, with all its mystery and precision and quiet strangeness, be the last thing on your mind as you drift off. It'll still be there in the morning, humming along beneath everything, the way it always has been, the way it always will be.